Hi again. I'm gonna start saying howdy. How you doing? Hello guys. How do you do? Good morning. Good day. Anyway, look at this problem here. It looks a mess, right? But don't get scared. I mean, just look at that and see what they are asking you to do. Determine the angles theta and phi or phi between the wire segments. So this angle and this angle. Every single time, no, almost every single time that a problem is asking you for an angle like that, what the problem is screaming at you, is yelling at you. Whenever you see this, the problem is screaming at you to use dot product. That's it. Where is the U? Here, dot product. Uh, and I imagine that you already went through the definition of dot product, but there are two definitions for dot product. If you say as a vector, vector A dot product vector B, you can say this is the magnitude, this is the scalar approach, magnitude of A, magnitude of B, times cosine of the angle between the two. You have A and B, and this is the angle. That will be one of the definitions, and the other definition is if you are doing, I'm going to use it in AI plus AJ plus AZ or AK multiplied by BI plus BJ plus BK. That will be AI times BI, so AI times BI plus AJ times BJ plus AK times BK. So there are two definitions. This is the vector type definition and this is the scalar definition. But remember, every time that you do the dot product, that's a scalar. That's basically it. Also, whenever a problem asks you what is the projection of this force on this axis, dot product. What is the how much of this force acts on this particular direction, dot product. Every time that you see that part, angles, projections, direction, how much of these acts on these, the problem basically is telling you that you have to use dot product. And either way, we're gonna need, if you see these, A, B, and magnitude of A, magnitude of B as a vectors between the wire segments. And one of the things that is important, and I'm sorry, I know I'm stuttering here, but one of the things that is important is when you do the dot product, the vectors have to be in this way, like that, tail to tail, together, tail to tail, like that, tail to tail. Meaning, if I want to find this angle, I need the vector BA and a vector in the direction of BC. But if I need this one, I need vector in the direction CB and a vector in the direction CD, like that. Because otherwise, if I just put the vector in this way, what I will be calculating is the other angle, not this angle, the exterior angle. So tail to tail, all the time. That means what? That means we need the coordinates of the points. What are the coordinates of the point A? 0, 0, 0. Where are the coordinates of the point B? In X, 0, because obviously you can see the point B is over this plane. So the coordinates of the point B will be 0 in X. In Y, it's going to be 0 0.4, 0 0.4. And in Z, it's going to be 0 0.5. What are the coordinates of the point C? In X, it's going to be this, 0 0.8. In Y, it's going to be this, 0 0.6. And in Z, it's going to be 0 because the point C is over the XY plane. So I have these, I have these, I have these, I need these. What are the coordinates of the point D? Well, the point D goes exactly over the y-axis, meaning it's going to be 0. This distance, which is 0 0.4 plus 0 0.2 is 0 0.6, and 0 in the z-axis. The rest, just find the projection, the position vector. So let's find a vector, the position vector BA, meaning coordinates of A minus coordinates of B. Coordinates of A minus coordinates of B. Coordinates of A 0, 0, 0. Coordinates of B 0, 0 0.4, 0 0.5. So this is going to be 0 in I, 0 0.4 in J, negative, because it's 0 minus that, and minus 0 0.5 in K. That will be the position vector BA. We are going to need the magnitude of that. So let's calculate the magnitude of BA. BA, magnitude of BA will be 0 0.4 square plus 0 0.5 square root 0.64. 0.64. And the units are meters, so we can put the units at the end. Now, we're going to need also the position vector BC. Position vector BC, it means tail, tip minus tail, always. C minus B, not B minus C. C minus B. What are the coordinates of the point C? 0 0.8, 0 0.60. So it's going to be 0 0.8 minus 0, 0 0.8 I, 0 0.6 minus 0 0.4, meaning 0 0.2 J, and 0 minus 0 0.5, that means minus 0 0.5 K. That's the position vector BC. BC, correct. Now let's calculate the magnitude of that, because we're going to need the magnitude of BC. And it's going to be just the square root of this square plus this square plus this square, 0.8 square plus 0.2 square plus 0.5 square to the 0.5, 0.964, 0.964 meters. What else? I could calculate this immediately, but let's keep going. Now I need the position vector CB. Position vector CB. Well, I don't have to calculate the position vector CB again, because I know the position vector BC is going to be the opposite of the position vector CB. So it's going to be just the same one, but with different signs. And the magnitude is going to be the same. So with these two, we're going to calculate this angle. Now I need position vector CD. Coordinates of D minus coordinates of C. What are the coordinates of D? 0 minus 0 0.8. 0 minus 0 0.8 minus 0 0.8 I. 0 0.6 minus 0 0.6, 0. 0 minus 0, 0. So this is going to be just the position vector CD. And the magnitude of the position vector CD will be 0 0.8. And with these two, we're going to calculate this angle. Now we apply both definitions for dot product. We're going to say that the vector definition, which is this one, has to be the same as the scalar definition. And then we will solve for cosine of the angle. Let me explain you. If I have to find RBA times RBC, RBA times RBC, I'm going to put it here. RBA dot RBC as a vector has to be equal to magnitude of RBA times magnitude of RBC multiplied by cosine of the angle. And then I can solve for this. I pass these magnitudes to the other side. What is this definition? That definition will be this I times I, J times J. I'm going to put the first one by steps. So RBA is negative 0.4 J minus 0.5 K. dot multiply by BC, 0.8I plus 0.2J minus 0.5K. And that has to be equal to what? Magnitude of BA, 0.64, magnitude of BC, 0.964 times cosine of the angle. Let's solve this. I dot I, but I is 0 here, 0I. So I dot I will be 0 minus 0.4 times minus 0 j dot j, right? Minus 0.4 times 0.2 minus zero point 0.4 times zero point 0.2 minus 0.4 times zero point 0.2 minus 0.5 times 0.5, which is plus 0.5 times 0.5, and then we get 0.17. So 0.17. By the way, the units of these are meters, and the units of these are meters. So if you like putting units, so this will be meters square. I'm gonna put the units. I shouldn't, but meters square has to be equal. Now let's work with the other side. These are meters also, and these are meters also. So then that will be 0.694 times 0.64 times 0.964. That would be 0.661696 or 0.617 meters squared, because this is mirror, cosine of the angle, and these cancel out. When I pass this dividend to the other side, I get that the cosine of the angle will be 0.17 divided by that value. That would be 0.2755, which means the angle will be inverse cosine of that. That will be 74 degrees. Done. Now for the second one, it's the same, but now I work with these ones. So RCB times RCD, that will be I dot I, 0.8 times 0.8, minus times minus is plus 0.64. J dot J, 0, K dot 0, 0 has to be equal to 0.964 times 0.8 cosine of the other angle, which means the angle in this case will be 0.64 divided by this is 0.64 divided by 0.964 divided by 0.8. So that will be the cosine of the angle, and the inverse cosine of the angle would be 33.91 degrees. Do this on your own step by step so you can see what is happening there. You see, it's a really nice problem also, and really easy to do once you know what you have to do. Thank you for watching, guys. See you in the next video, or as I always say, better said, you will see me in the next video. I will imagine that I'm seeing you in the next video. Have a good day.